Hi guys. Okay, so let us look at the measurements. So when we are taking measurements, we are working with numbers. There are two ways of writing the numbers. One is the standard notation and the other is the scientific notation. Commonly, we write the numbers in the standard notation. The big numbers such as this, 25342, and then the small numbers such as 0.000253 are signifying some kind of measurements, whether that measurement is in the terms of length or mass or volume or molarity or those things. But the problem comes when the measurements become either too large or too small. In other words, when we are dealing with lots of numbers, then they are occupying a lot of space on the paper. And when we are dealing with very small numbers, then of course we have lots of zeros in front of the actual numerical digits. And these occupy the space as well. So how do we condense them? So scientific notation is used to write the big numbers in a condensed form and the small numbers in a condensed form. Now here you see this number, which is 25,342. We do not see a zero here and we do not see a decimal. So let's just look at the decimal and moving the decimal first of all. So the decimal is not seen, but it is present, it is implied, it is after 2. This is an exact number, okay? So we move the decimal to the left. And for a scientific notation, keep this in mind that we need to have the first digit and the decimal goes after that, and then comes the next digit. So it's always the first digit, and then the decimal goes after that, and then whatever numbers we want to keep, and that's fine. So in this case, we move the decimal 4 places to the left. And in that case, when we move 4 places to the left, we bring the coefficient. So here, this is the 10 raised to the power 4, because we moved 4 places, and the decimal moved 4 places. So it is 10 to the power 4. So 2.5342 into 10 to the power 4 becomes the scientific notation of this number, which is originally 25,342. The next number, 0.000, so there are 3 zeros and then 253. So we are moving the decimal from the very first point to after 2. So here we move the decimal 4 places to the right. So when you move 4 places to the right, in that case, this is again becoming 10 to the power -4. Negative signifies a small number and positive signifies a big number. Okay, so the number now becomes 2.53 into 10 to the power -4. So it still means the same. It still remains a small number, but the method of writing has changed. In other words, it's a condensed form. Okay, so these are the two ways, you can write the big and small numbers. And small number. Okay, next is the commonly used units. Now, when you're taking the measurements, in what context are you using those numbers, or in what context is the measurements being made? So it could be length, as I said, could be mass, could be temperature, could be time, could be volume, and could be the amount. And there are many more, but these are commonly used. So these are the base. These are the commonly used the base units. Okay. Now for the unit, for length, now there are two actually methods, or two types of units. One is the international unit called the SI unit. Okay, international unit is the SI unit, like in other words, it's a standard. It's more of a standard which is followed in different countries. Okay, different countries follow them and some countries don't, but this is to bring uniformity in the measurements. Okay, so SI unit is one, and then the metric is also another one, and SI and metric kind of interchange. Okay, so for example, for length, the unit of meter is represented as m, and it is both used in the SI and the metric system. The unit of mass in the SI system is kilograms. Okay, in the SI system is kilograms, and it is kilograms is written as kg, and then the grams is written as g, and that is a metric unit. Next is the temperature. The temperature has degree Celsius, degree Fahrenheit, and Kelvin. So Kelvin is written as K, that's the abbreviations, the symbols, right? And then SI unit, but the metric system uses the degree Celsius. Then comes the time. The SI and the metric unit prefer second. Okay. Then comes the volume. Volume is more of a derived unit because it's coming through, measurements. In the SI system, it is the meter cube, and in the metric system, it is the liter. Okay, and later on, we will see that, these are kind of like in what context the measurement is being done. So is it a volume of a solid? If it is a solid, then it's meter cube or centimeter cube. But if it is a liter, then we use it for the liquids. Okay, now another unit which applies to the number of particles, the number of atoms, the number of molecules, that's the mole, and that is used in both the SI and the metric system. Okay, so that is the way we use these units in the different systems, the SI and the metric. But then the US system also is more commonly used as the US system in US, which does not follow the SI. So what is that? So here is this again, the same thing, the base units: length commonly measured, mass commonly measured, volume and time commonly measured, right? So here for the length in US, we use mile, we use inches, we use feet. And then the short form for miles is MI, the short form of inches is IN, and the short form for feet is FT. For mass, we use pounds and we use ounces. For pounds, we use LB as a symbol or a short form, and for ounce, we use OZ. For volume, we use quarts and we use pints. So for quarts, we write QT, and for pints, we write as PT. For time, we use hour, okay? We use hours, and we also use minutes, okay? So that's the US system. Now, before we go further into equalizing the US system and the metric system, first, let's look at the common prefixes that are used. The prefixes is something that is written before the base units. So we have seen kilo, we have seen mega, we have seen giga, and we have seen tera. Kilo stands for K, mega is M, giga is G, and tera is T. Kilo is a big unit, so it's 10 to the power 3. Anything that is 10 to the power 3 is kilo. Anything that is 10 to the power 6 is mega. Anything that's 10 to the power 9 becomes giga. Anything that is 10 to the power 12 is tera. For example, if you have 3 kilometers, it means 3 into 10 to the power 3 meters. If we have 3 megahertz, it means 3 into 10 to the power 6 hertz. HZ is hertz, okay? If we have 3 giga years, it means 3 into 10 to the power 9 years. If we have 10 terabytes or 10 terawatts, that means, or 3 terabytes or 3 terabytes, in other words, or 3 terawatts, it means 3 into 10 to the power 12 watts. Okay, so these are just some examples, but just keep this in mind that these 10 to the power, these coefficients of 3, 6, 9, and 12, these relate to these positive, these relate to very big units or very big measurements. Now, when you're measuring something small, then you use these units. Deci is shown as D, and it means 10 to the power minus 1. Centi is C, 10 to the power minus 2. Milli is M, 10 to the power minus 3. Micro is micro, the sign micro, the Greek symbol, 10 to the power minus 6. Nano, N, 10 to the power minus 9. pico, P 10 to the power minus 12, femto, F 10 to the power minus 15. Okay, and so these negative exponents mean that these are small measurements. Now we are going to look at the equalities. So in other words, conversions within the metric system, conversions in the US system, and then in converting the metric to the US and US to the metric. So these are called the equalities. So now we are going to look at the common equalities in volume. In volume, 1 liter is 1000 milliliter. 1 deciliter is 100 ml. 1 milliliter is 1 centimeter cube. These are just some examples I'm giving you, but there are more. In US, for example, 1 quart is 4 cups, 1 quart is 2 pints, and 1 gallon is 4 quarts. And then how do you convert something that is in a metric to the US or US to metric? You equalize the two. So 1 liter is 1.06 quarts, or 473 milliliters is 1 pint. Same is the story with the mass. 1 kilogram is 1000 grams. 1 gram is 1000 milligrams. So commonly you are going to use this 1 gram and 1000 milligrams in the chemistry classes. So 1 pound is equal to 1 ounce. That is a US system. And to equalize metric and the US, so we have 1 kilogram, which is equal to 2.20 pounds, or 454 grams is equal to 1 pound. So these equalities again are also given in many different tables in the books, and there are many different other equalities listed. I'm just giving a few examples here. Length, for example, is 1 kilometer is equal to 1000. Anytime kilo comes, 1000 millimeter, 1000 meter, but 1 meter is 1000 millimeter. Millimeter is a smaller unit. So small 1000s make 1 meter. That is in the meter conversion. US conversion, 1 feet and inches. 1 feet is 12 inches. 1 yard is 3 feet. 1 mile is 3280 feet. Okay, and then converting metric to US is 2.54 centimeter is equal to 1 inches, or 1 meter is equal to 39.4 inches, or 1 kilometer is 0.621 miles. So these are the conversions of metric and US. So we call them equalities. Now, in order to convert an equality, generally, or something that is given in one unit to another unit, we use the method of conversion factors. So whatever units you are given, you place them on the left-hand side, and then you bring the conversion factor, in which in the numerator, you put the units that the question is asking, or the numerator contains the units that you want, and the denominator contains the units that you want to get rid of or you want to remove. So that when you are placing it in the bottom of the, in a fraction, then they get, canceled out. So this way, okay? Now, next we are going to look at the significant figures. What are significant figures? Most commonly, we call these significant figures SF or sig figs, like short, okay? So there are 3 rules here. One is a number is a significant figure. Significant figure means important. So when you're making some measurements, right? So you have to deal with, what is important and what is not. And before we come there, let me just cover this part. Accuracy, precision, and uncertainty. Let's look at that. So when we are doing measurements, yes, we want to be as accurate as possible. So for example, here we have water, and water has a meniscus, right? The bottom part is the one that is touching the, about the 3 ml part. So that's what you need to measure. But there is a difference. There are tall people can look at the number from the top. The person from the bottom can look at it, the short height can look at the number from the apparatus from the bottom. And a person who's a middle-aged is going to look at it maybe at the eye level. So now middle height, sorry. So it comes problem here that who is right? The person looking from the tall person, a short person, or a medium height person. So, due to that, some errors come into our measurements, okay? And that's why they can impact the accuracy, precision, and they can bring in some kind of uncertainty. Also, when you are measuring things with a ruler, right? When you measure things with the rulers, there are two types of rulers. One is very, very exact. So you can like measure in between those like demarcations. But some of the rulers are just like where you have to estimate. So once you start estimating, that's where you have the uncertainty in the system. So that's why, so that's why the significant figures comes into play, where you can just follow certain rules and go from there. What is accuracy? Accuracy is, there are generally in the labs, or we have a true value. A true value is a known value. This known value is the value that is known to the stock room of a solution, of the unknown compounds or whatever. So that's known to the professors and to the managers in the stock room. That's the true value. This true value can also be the information that is already known to the public. It is listed in the Google searches, in the tables, so that's known. Like the density of substances, known, boiling points of the substances, known already, right? So that you can obtain through the Google searches, or you can look at the books, you can look at the appendix in the books, or all that information is also listed there, depending what you're working on, whatever lab you're working in. So those things. Anyways, so those are the true values. Now you're working with an unknown sample and you're trying to determine the value you're measuring, or you're determining the value of the sample, and you're gathering data. When you gather data, you follow some steps in an experiment. So with all those steps, and then you try also first trial, second trial, third trial, and so forth. So when you have the first experiment, first step, first trial, not the step, the trial, right? You finished all the steps and you have a trial, you get a certain number. Now you repeat the experiment. If you get the exact same number, and then you repeat the experiment again, in the third trial also you get the exact same number with a little variation here and there, but the range, in that reasonable range. And these values match with the true value. That means then your data is accurate and your data is precise. Okay. And it falls in that range of the true value. So your data is accurate as well as precise. But next is, if you have a value that is not close to the true value, you did trial 1, trial 2, trial 3, you get exact, more or less the same results, but they do not match the true value. What does this mean? This means that your data is not accurate, but it is precise. Means that you have made the same mistakes in all the steps. So you need to figure that out. What mistake did you make in all the steps? Next is, sometimes you try to see, okay, you did trial 1, you get some data. You repeat the experiment, you do the trial 2, you get a totally different results. You do trial 3, you get a totally different result. So in this case, your data is neither accurate nor precise. In other words, you are making mistakes in each of the trials. There is a mistake. That is why neither of those trials have produced the results similar to the true value. Okay, so these are the things that we do in the labs, where we deal with the data and we gather data. So that's where the rules regarding the significant come into play, where when we are doing the measurements, how much of the uncertainty, or how much of the uncertainty is like this here. When you're taking a measurement, right? And so here you have a scenario where you have like a water level is a little bit above 3, but then it's not, because there are no proper markings in this container. So we don't know. We are just guessing. It could be 3.6 ml. It could be 3.5 ml, or it could be 3.4 ml. Okay, so now we are uncertain. So that's where, we have these significant figures, rule of significant figures that come into play, where we know exactly, okay, fine. How should we, what is a tolerance, or what figures are important? We should exactly have that level of measurement. After that, we can deal with some kind of ambiguity or uncertainty. How sensitive is this? calculations. For example, people who are working in the engineering field, for them, measurement should be exact and very precise. But people who are working in the kitchens, fine, they can deal with a lot of estimation also. So for them, uncertainty is tolerable up to a certain level, right? That's, you can deal with little bit of uncertainty. But for the engineers who are trying to, or architects who are trying to build these houses and bridges and so forth, for them, the tolerance for uncertainty may be, very low. Okay, so the rules are all non-zero numbers are important or significant. In other words, when you're doing the measurements, then all the numbers, if there is no zero, then you measure all of them. So for example, you have a number here, like, let me just get some examples here. All right, so for example, you have a number like a non-zero number, like for example, like 3.268. So how many significant figures are there? In other words, 1, 2, 3, 4. These 4 numbers are important, are significant. Okay. For example, if you have 3, 2, 6, 7, 8, in that case, 1, 2, 3, 4, 5 significant figures. These are important. So all these non-zero numbers are important. If you have a 0 in between the 2 non-zero numbers, for example, you have a number such as 2005. So this is the 0 that is in between. It's a captive 0. It's in between. So these numbers, 1, 2, 3, 4. So these are 4 significant figures. All these zeros are counted, in other words. They are important. Okay. On the other hand, if you have something with a decimal like 6.00027, so in that case, what will you do? All these zeros are important or counted. 1, 2, 3, 4, 5, 6. So there are 6 significant figures. So they are counted. Okay. So 0 in between the 2 non-zero numbers. Okay. Next is 0 in a decimal number is counted. So remember, all these numbers are significant figures. These are important. The number is a significant figure. It's important that 0 is counted. The 0 in a decimal number, like for example, you have a number like 10 point liters. What does this mean? This means that it has to be exactly at 10, not 10.0, not 10.1, not 9.99 or something, exactly 10. That's exact measurement. So you see, so in this case, we have 1, 2 significant figures. Okay, if you have a number like this, 5, 3.02. So in this case, we will see that 1, 2, 3, 4. So when you're doing the measurements, you're taking a ruler and measuring that it should go up till 0.02. And after 2, it can fluctuate, and that's fine. So this is the 4 significant figures in this case. If you have a number like here, sorry about that. Sorry. Oh, sorry about that. That's why during the daytime it's kind of tricky. Okay, anyway, so let's look at this number. You have 19.00. In this case, when you're doing the measurement, it should exactly 9 and 2 places after the decimal. Nothing more, nothing less. So in this case, we have 4 significant figures and so forth. You can go. Then the coefficients in a scientific notation, those are important. They are not counted, but they give a value to the number. So for example, you have a number 2.8 into 10 to the power 5 meters. So yes, this is counted, this is important, but it is not like, it's not counted, but it has its own value. Because remember, back to, it can be written in the scientific notation and a number can be written in a standard form. So if you remove that 10 to the power 5, then it changes the value, the magnitude of the number. So here, these two significant figures. So measurements should be exactly at 2.8. If you have a number such as this, 5.70 into 10 to the power -3 grams. Okay, so in this case, because the decimal is there, right? So these zeros are counted. So this is 3 significant figures. Okay, and you leave that 10 to the power -5 because it tells you that 10 to the power -3, because it tells you that this is a small number. But those 3 significant figures are when you're doing the measurement, when you're taking a ruler or measuring or reading through a container or whatever, even on the thermometer, even on the weighing scale, then that number should be 3 places, you know, on that reading device. Now 0, that is not significant, which is not important. I mean, okay, here's the thing. It doesn't make sense though that it is not important. It is still important, but at least in the terms of, you know, doing measurements, counting, we can ignore them. That's a better way of saying that. So here we have this number that is not important, is like here zeros, 0, 0, 0, 0, 5. So you see this number 1, 2, 3, 4, and 5. These numbers can be dropped. In other words, these 5 digits, these are what are these called? Trailing, or, you know, the zeros that are in front. These can be ignored. I mean, in reality, it doesn't make sense, right? But for the sake of measurements, yeah. So that means this is only one significant figure. Okay, only take 5. All right. For example, if you have a number like 0.00750, remember, there's a decimal, right? So this number dropped, this dropped, this dropped. Ignore. Okay, when you ignore, but because there is a decimal, this 0 will be counted. Okay, so this is 3 significant figures. All right, now exact numbers can have variable significant figures because exact numbers can be written in scientific notation. Therefore, this number 100 can have 1 significant figure, can have 2 significant figures, and the maximum can have 3 significant figures. So it can have all 3 because these numbers can be written in scientific notation. If you have a number such as like 850 and then 000, so in this case, you have 1, 2 for sure, but then 3, 4, 5, 6, all variable, right? So this thing can have a maximum of like, will have like 1, 2, and then 3, 4, 5, 6. Is it 1, 2, 3, 4, 5, 6? Yeah, 6 significant figure. All the possibilities are there. Okay, so that is why the exact numbers generally are not even counted when we are doing the calculations. Okay, so now comes the rounding numbers, rounding up and down. Now think about it. In chemistry, we are dealing with matter, right? So when we deal with matter, the rounding down doesn't make sense because we are cutting off matter. So we just have to like you can do that. Okay, rounding up is fine, you know, is fine. So, but rounding down is not. So if you have to figure out your final answer, so first of all, never round down or round up or round or leave as is. Don't do the rounding in the steps because then you start introducing ambiguity or errors. only in the final answer. Next thing is, if the digit to be dropped is 4 or less, then you leave the number as it is. The number that is dropped, the number that is dropped, if it is 4 or less, the number that is retained on the left-hand side, you leave it as it is. But if the digit that is 5 or more, that is dropped, the number that is retained is if the digit to be dropped is 5 or more, then the number that is retained is you round it up. Okay, so that thing. Now, next is you only do it in the final answer. Next is the significant figures in calculations. When you're doing these calculations, when you're trying to figure out your final answer to the exact number of significant figures, you see if you're adding or subtracting. When you're adding or subtracting, whatever numbers you are using, you are going to count the decimal places. So the number that has the lowest decimal place, that influences the final answer. So your final answer should have the lowest decimal place that was in the computation. Next, when you're doing multiplication and division, in that case, the answer should hold the lowest significant figure that was in the computation. Okay, so these are the very basics of, measurements. And now we are going to look at the examples. So for now, I am going to stop recording and we will look at the examples in the next video. Thank you for watching. Bye.